Hello again and welcome to a new video lecture in which we will discuss support conditions in 2 dimensions for rigid bodies. In order to do so, we need to again recap the idea of a free body diagram, which is a very important concept in solving an equilibrium question. So, in order to draw this diagram, the first thing and the most important thing that we need to decide is which is the body that we need to consider. So we need to consider this body from all the system and take it out, isolate it, and then draw it. And once we've done that, we need to draw all the forces, meaning both forces and moments that act on the body. And then we should show all the dimensions, and we have to select the system of coordinate axes before we can write the equations of equilibrium. However, bodies are also supported in order to achieve equilibrium. So let's talk a little about support conditions for bodies in 2 dimensions. Now, the role of the support conditions, the main role of the support conditions, is to connect the bodies to, let's call, the environment. That could be another body, could be the ground, could be a wall. So it helps the body achieve equilibrium by transferring forces from the body to this so-called environment. In order to study equilibrium of the body, we have to remove the body itself from the supports and replace the supports with corresponding forces. How do we do that? Well, we always have to remember and apply Newton's third law of motion, the action and reaction. So for every action, there's an opposite and equal reaction. However, the general rule that you need to know and remember is you have to add a force or a moment when you remove a support for every translation and rotation, respectively, that is not permitted by the support removed. So in other words, you have to decide, when you look at a support, as a specific support, you have to decide what movements, what degrees of freedom in terms of translation or rotation this support does not allow. And then for these, you will have to replace them with either forces for translations that are not permitted, or with moments for rotations that are not permitted by the support. So again, this is a very important rule. If you remember this rule, and if you think how the supports work, you will be able to very easily replace the supports with their corresponding internal forces, also called reaction forces. So let's look at a few typical examples of supports or support conditions, and the ones that I'm going to show you here are the representative ones. So I strongly suggest that you also refer to the table for supports for rigid bodies in 2 dimensions that is given in the textbook. So I'm going to start with the first and simplest support, which is a roller support. It's called a roller support. This is the diagram of this support. So it's like a little triangle on 2 wheels. And what this support does, you see, it resembles a little like a car on the road. It allows translation in the horizontal direction. It allows rotation around its point. However, it does not allow vertical translation in any direction, both upwards and downwards. So when we draw the free body diagram of the part of the body that is shown here, we have to replace the degree of freedom which is not allowed, the vertical translation, with an unknown force, which is the one in blue. In this case, a reaction force that is vertical. A second support that we will look at is what we call a slider. And you will see that in certain respects a slider behaves in a similar fashion as a roller. So let's draw first a slider, which is virtually like a collar that can slide along a rod. So you can see the collar here in the middle. I'm going to use a shade of black to emphasize it, and the rod is the horizontal bar along which the slider can slide. So it can slide again in the horizontal direction. It can rotate if the collar is narrow enough, but it cannot move vertically up and down. So to replace this support, we only have to add a vertical reaction force corresponding to the vertical degree of freedom that is not allowed by the slider. A pin support, sometimes also known as a hinge, is drawn very similarly using a similar symbol as the roller, except those two little wheels are gone now. And a pin support allows rotation around the pin, but it does not allow translations in both the horizontal and vertical directions. So to draw the free body diagram of the body, we have to remove this pin support and replace the blocked degrees of freedom with horizontal and vertical reaction forces. Next, the fixed support. So as you can see in the diagram that I'm just drawing now, a fixed support shows just the hatched base, and a fixed support, as you can imagine, does not allow any movement. So all the 3 degrees of freedom in 2 dimensions are not permitted. Therefore, the fixed support will be replaced with 3 reaction forces, 2 actual forces accounting for the blocked translations, and 1 moment force accounting for the blocked rotation. Another example is if we deal with a cable or a rope, which has to be in tension, in other words, has to be stretched. You can only have tension forces in a cable. You cannot have compression forces in a cable because, as you can imagine, you cannot push on a rope. It will just go simply slack. So what's happening in a cable? If we draw the free body diagram of 2 segments of the cable after cutting the cable at the middle, then you will see that there's an internal force running along the cable which is in tension, and that would be the force that you have to replace the other half of the cable with. Now, often in questions we would have bodies that are in contact, touching each other. In other words, one body supporting the other one, and if we need to analyze one of them, we need to separate them. In between these bodies in contact, the translation that is perpendicular to the common tangent is always not allowed, and sometimes if friction is existing, is not zero, then you'll also have a tangential force, which is the friction force. So now if you were to separate the bodies and draw the free body diagram, say of the left hand body, then you have to replace the other body, with a first normal force, which is perpendicular again to the common tangent, and that force is always there. And with sometimes a friction force, which runs along the tangent, the common tangent, and then you'll have both the normal force and the friction force if the surfaces are rough, so if there's friction present. Another case is that bodies typically have a mass and therefore a weight. So we'd have to know how to represent the gravity force. And this will always act on the body in the vertical direction and down. So we always know the direction of this force. Vertical and downwards. Now the last case that I would like to mention is spring action. So when bodies are connected to the environment by a spring. Like for example this case here, in which we have a body, a spring, and the spring is connected to some rigid support. What can happen now? The body can be forced, moved to the right, but that degree of freedom is resisted by the spring. So after the spring having elongated by distance x, then the spring will tend to pull back the body to the original position. Or one can push the body to the left. So in this case the spring will become compressed, say by x amount, and now the spring will react into the body and try to push the body to the right. So you see in both of these cases the spring reacts in the opposite direction of the movement. So therefore the magnitude of the reaction force F equals to negative k times x, and this is called the restoring force. Negative k, the negative sign is because of the movement happening into the opposite direction, and k is the spring elastic constant, which is specific to each spring. It's a characteristic of the spring. So this is what I wanted to tell you about different support conditions. I would like to thank you for watching this lecture, and I will see you again at the next one.